All right, so this is our definition for the complex numbers. And again, kind of cryptic looking. Does anybody remember talking about the complex numbers in your Algebra 1 class? There might have been one or two of us that have heard of this before, but it probably pretty rare. Be a good surprise if you had. We'll talk about this idea a lot in this first semester, but my assumption is that nobody's really talked about the complex numbers before. So, and we'll, in a moment, we'll talk a little bit about like why these, like what this is used for, why we built this other setup. But that's enough. I'm just going to write down the definition. We'll kind of move forward here. So let's just talk a little bit about the relationship between these 5 sets. So let's start first with the natural numbers and the integers. When I look at the set of natural numbers, I have the numbers 0, 1, 2, 3, etc. And if I look at the integers, what do you notice? I also have the numbers 0, 1, 2, 3, etc., right? You see that? That everything in the natural numbers is also in the integers? We have a definition for that. So we say A is a subset of B. And this subset symbol is like your inequality symbol, but it's rounded instead of pointed at the end. So we say that A is a subset of B if everything in A is also in B. So we can say that, I don't know why I wrote that symbol wrong up there. Sorry. If you noticed, you should have said something. Occasionally I make mistakes. It's okay if you correct me. So we have that the natural numbers are a subset of the integers, right? Everybody's okay with that idea? Yes. Oh, good. Thank you. I don't want to get confused. I don't want to confuse anybody. So let's try to be consistent, right? Good. Thank you. All right. What if we compare the integers and the rational numbers? Can I take every integer and write it as a fraction? Yeah, how would I do it? Just put it over 1. Yep, exactly. So it tells me the integers are a subset of the rationals. And now because I have that the natural numbers are a subset of the integers, and the integers are a subset of the rational numbers, I also know that the natural numbers are a subset of the rational numbers, right? That chain carries all the way down. Okay, what if I want to do the real numbers and rational numbers? Can I take every fraction and write a decimal expansion for it? Yeah, right? How do I do it? Divide the numerator by the denominator. Yeah. And now let's look at these complex numbers. So this A plus BI tells me what the things inside the complex numbers look like, right? Well, A and B are just real numbers. So what if B is equal to 0? Right? That's a real number. That means I'm going to have A plus 0 on. What's 0 times anything? 0. What's anything plus 0? Itself. Yep. So this is just going to equal A, right? And what is A again? Just a real number, a single real number. So all the real numbers are also contained in the complex numbers, right? Just means that that b part is 0, so all you're left with is a single real number. Oops. Or if you are a visual person, if you want to think about it that way, the smallest of these sets is the natural numbers, which is contained inside the integers, which is contained inside the rational numbers, which is contained inside the real numbers, which is contained inside the complex numbers. So that tells me that if I have something here, like the number 5, that's a natural number, right? But it's also an integer, and a rational number, and a real number, and a complex number, right? So just helps us kind of visualize what's going on there. Okay, so a little story here. Think back to elementary school. Think back to kindergarten, elementary school. What was the main skill you were worried about when you did math in kindergarten? Counting, right? Learning the numbers, counting, right? Even before you added, we had to count. Everybody's okay with that idea? Which set of numbers were we using when we counted? The natural numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? After we learned to count, we started adding, and after adding? Okay. When we added, did we need anything more than the natural numbers? No. If you add 2 natural numbers, you get another one back. If we subtract, do we need more than the natural numbers? Sometimes, right? Why? You could get a negative answer, right? 4 minus 5 gives you a negative number. So we extended the set of numbers we worked with to the integer so we could deal with negatives, right? After you learned addition, subtraction, what came next? Multiplication and division. If you multiply, do you need anything more than the integers? If you multiply 2 integers together, you get another integer back, right? What if you divide? You need more, right? You need to have fractions. You need to have things that could be written as either a repeating decimal or a terminating decimal, aka a fraction. So now we're extending to cube. After you learn to multiply and divide, next thing we started doing was like solving, right? To solve x squared equals 2, what are you going to get? Like the square root of 2? Irrational number, something that can't be written as a fraction. So we extend it again to the real numbers. In this class, we're going to solve things like x squared equals negative 2. The answer to that is a non-real number. We're going to extend out to the complex number so we can answer those kinds of an equation, or those kind of questions. So the question to me is, we have this mathematics, right? Was this created or was it discovered? I don't know. It's a philosophical question, but it certainly seems like every time we've needed to solve a different kind of question, we extended what we did before to include everything we were doing before, but then allow us to do something else new. And that's the big pattern behind all of mathematics. Take what we already know how to do, extend it a little bit, so we can do a new kind of problem that we weren't able to do before. Anyways, that's all I have for you guys. I have no homework for you tonight.